Okay, so for each of these integrals, we want to find a simpler integral that we think might behave like the given integral, and then use the comparison test to show that the given integral converges or diverges. So we've got a little reminder of to show convergence, you need a larger integral that converges, and to show divergence, you need a smaller integral that diverges. So the integral from 1 to infinity of 5 over e to the x plus 1. Well, that is the same thing as 5 times the integral of 1 over e to the x plus 1 dx. Now the 5 doesn't matter. If that integral is finite, 5 times a finite number is still finite. If that integral is infinite, 5 times infinity is still infinity. So the 5 doesn't matter at all. So I just need to decide whether this integral converges or diverges. Okay, so I'm going to compare to the integral from 1 to infinity of 1 over e to the x dx, which I know converges. Okay, you have earlier in the packet a list of integrals that are useful comparisons, and the integral from a positive number to infinity of 1 over e to the x dx is one of them, and we know it converges. Okay, so I'm going to compare e to the x plus 1 to e to the x. So the denominator of my integrand to the denominator of the comparison integrand. Okay, so e to the x plus 1 should be bigger than e to the x, which means that the reciprocals, 1 over e to the x plus 1 compared to 1 over e to the x, should be the reverse inequality. A larger denominator makes a smaller fraction. So my integrand, 1 over e to the x plus 1, is smaller than a convergent integrand. So let's write out a sentence of what we have here. I'll do it over here. So the integral from 1 to infinity of 1 over e to the x plus 1 dx is smaller than the integral from 1 to infinity of 1 over e to the x dx, which is finite, right? So the integral I'm curious about is smaller than a finite integral, thus it converges. By the comparison test. Okay, the integral from 1 to infinity of 1 over the square root of x to the 5th plus x dx. I'm going to compare to the integral from 1 to infinity of 1 over, I'm just going to look at the leading term here, the square root of x to the 5th, which is the same thing as x to the 5 halves, which I know converges. Okay, because that's 1 over x to the p. The integral from a positive number to infinity of 1 over x to the p converges whenever p is bigger than 1. Okay, so now I need to compare, I'm going to compare the denominators first. So the square root of x to the 5th plus x compared to the square root of x to the 5th. So the left-hand side should be bigger, right? Because I'm adding x, which is a positive number. So it should be bigger when you add x to it. And then when I take the reciprocals, the inequality reverses. So my integrand is smaller than the integrand of a convergent integral. So I'm going to write out my conclusion. Do it in a different color. So the integral from 1 to infinity of 1 over the square root of x to the 5th plus x dx is smaller than the integral from 1 to infinity of 1 over x to the 5 halves dx, which converges. So if my integral is smaller than a convergent integral, it has to also converge. So the integral from 1 to infinity of 1 over the square root of x to the 5th plus x dx also converges by the comparison test. Okay, this one's a little trickier, so we have a hint written out here. The integral from 1 to infinity of 2 plus cosine x over x dx. So the hint is to know that cosine x is always sandwiched between -1 and 1. The, the outputs of the cosine function are always between -1 and 1. So cosine x plus 2, if I add 2 to all three pieces of this inequality, plus 2, plus 2, plus 2, I get 1 is less than or equal to 2 plus cosine x is less than or equal to 3. And then if I divide all three pieces of that inequality by x, 2 plus cosine x over x should be larger than 1 over x and smaller than 3 over x. So one side of that compound inequality will help us prove divergence. So 1 over x and 3 over x are both divergent integrals from 1 to infinity. So I need my integrand to be larger than something divergent. So my integral, the integral from 1 to infinity of 2 plus cosine x over x dx, is larger than the integral from 1 to infinity of 1 over x dx, which is infinite. Which diverges, right? It's in the area under the curve 1 over x dx from 1 to infinity is infinite. So the area under the curve 2 plus cosine x over x from 1 to infinity is more than that, so it has to also be infinite. Thus, by comparison test, the integral from 1 to infinity of 2 plus cosine x over x dx also diverges. Okay, the integral from 3 to infinity of 1 over e to the x ln x dx. Okay, so I know the convergence behavior of 1 over e to the x, so that's going to be my comparison. I'm going to compare to the integral from 3 to infinity of 1 over e to the x dx. That is a piece of my integrand, and I know that it converges. So I'm going to compare e to the x ln x, the denominator of my integrand, to just e to the x, the denominator of the comparison integrand. So my x's are between 3 and infinity. Those are the bounds of integration. So e to the x times a positive number that's bigger than 1 should yield a result that's bigger than e to the x. So when x is larger than e, ln of x is a number bigger than 1. So that is true. And that means that the reciprocals reverse the inequality. Larger denominator makes a smaller fraction. So my integrand is smaller than a convergent, the integrand of a convergent integral. So it has to also be convergent. So conclusion is that my integral from 3 to infinity of 1 over e to the x ln x dx is smaller than the integral from 3 to infinity of 1 over e to the x dx, which converges. Okay, so thus my integral must converge also. By the comparison test, the integral from 3 to infinity of 1 over e to the x ln x dx also converges. Okay, this one we're going to do two ways. First, we're going to use the comparison test, the integral from 1 to infinity of 1 over x squared plus 4 dx. So I'm going to compare to 1 over x squared, the integral from 1 to infinity of 1 over x squared dx, which converges. So let's compare the denominators. X squared plus 4 compared to x squared. Well, x squared plus 4 should be bigger, which means the reciprocals, 1 over x squared plus 4, should be smaller than 1 over x squared. Larger denominator, smaller fraction. So my integral is smaller than a convergent integral, which means it converges. So in conclusion, the integral from 1 to infinity of 1 over x squared plus 4 dx is smaller than the integral from 1 to infinity of 1 over x squared dx, which converges. Thus, the integral from 1 to infinity of 1 over x squared plus 4 dx also converges by the comparison test. All right, we're going to do this a second way. We're going to evaluate the improper integral directly using a trig substitution. Okay, so let's remember the integral was from 1 to infinity of 1 over x squared plus 4 dx. So I'm just going to work on the indefinite integral for a minute. So drop the bounds of integration. I just want to find an antiderivative for 1 over x squared plus 4 dx. So we use a trig substitution. This is x squared plus a squared, which indicates we should use x equals 2 tan theta, which means that dx is 2 secant squared theta d theta. And then I sub into my integral. So this is the integral of 1 over, instead of x squared, it is 2 tan theta squared plus 4, and instead of dx, it is 2 secant squared theta d theta. Okay, so now I'm just going to do some algebraic manipulation on the integrand. So this becomes 1 over 4 tangent squared theta plus 4. And then I'm going to factor out a 4 from the integrand. So this is the integral of 1 over 4 times tangent squared theta plus 1 times 2 secant squared theta d theta. And tangent squared plus 1 is equal to secant squared. So what I have in parentheses here, tangent squared theta plus 1, cancels with my secant squared theta. And all that's left after that cancellation is 2 over 4. So this is the integral of 1/2 d theta, which is 1/2 theta plus c. Now I just have to plug in what theta is equal to, and that comes from the original x equals 2 tan theta. So if x equals 2 tan theta, I'm just going to solve for theta. So x over 2 equals tan theta, which means that theta is the arctan, or the inverse tan, of x over 2. So my antiderivative is 1/2 arctan of x over 2 plus c. So that's my antiderivative. Now I'm going to do the whole definite integral with the bounds of integration, now that I have an antiderivative. Scroll way back up to the original integral. So instead of integrating from 1 to infinity, I'm going to integrate from 1 to b and take a limit as b goes to infinity. So this is the limit as b goes to infinity of the antiderivative of 1 over x squared plus 4, which I just found out was 1/2 arctan of x over 2, evaluated from 1 to b. Limit as b goes to infinity of, when I plug in a b, I get 1/2 arctan b over 2, and then I'm going to plug in a 1, and I get 1/2 arctan of a half. There we go. Okay, so now I'm going to take the limit as b goes to infinity. So the arctan of b over 2 as b goes to infinity, that's the arctan of infinity. So I have to think about, where is the tangent undefined? Where does the tangent approach infinity? And that happens at pi over 2. There's a couple of ways to think about it. One way is to think about the graph of arctan. So if I just quickly draw a sketch down here, 0, pi over 2, negative pi over 2. The arctan function looks like this. Asymptotes at pi, multiples of pi over 2. So I'm looking at where is the arctan infinite, and that happens at pi over 2. So as b goes to infinity, the arctan of infinity would be pi over 2. So when I evaluate this, I get 1/2 times pi over 2, which is pi over 4. And then my second piece here has no b's in it at all. It's just 1/2 arctan of a half, which isn't a special value, so I'm just going to leave it like that. And that is finite. It's just a number, which means that the interval converges, the integral converges. Sorry, this is not arctan that I drew. This is tangent. This is y equals tangent of x. So I was looking for outputs of tangent that were infinite, and the input that gives that is pi over 2. So the arctan of infinity is pi over 2. Okay, so I want to first evaluate whether this integral converges or diverges using the comparison test. And I have the integral from 2 to infinity of x over x squared minus 1 dx. So I'm going to compare to 1 over x. I'm going to look at the leading term on the top and the bottom, and that's x over x squared, or 1 over x. And I'm looking from 2 to infinity, which diverges. Okay, so now I want to compare the integrand to 1 over x, which is equivalent to x over x squared. So if I have x over x squared minus 1, I want to compare that to x over x squared, which is the same thing as 1 over x. Okay, so my numerators are the same. They're both x's. My denominators are close. X squared minus 1 versus x squared. X squared minus 1 is smaller than x squared, right? Subtracting 1 should give you a smaller value. A smaller denominator leads to a larger fraction. So my integrand is larger than 1 over x, which means that my integral is larger than the integral of 1 over x, which is infinite. So let's write out the conclusion. The integral from 2 to infinity of x over x squared minus 1 dx is larger than the integral from 2 to infinity of 1 over x dx, which diverges. So my integral diverges also. By the comparison test, the integral from 2 to infinity of x over x squared minus 1 dx also diverges. Okay, last bit, I want to directly evaluate this improper integral using a u substitution. So the integral is 2 to infinity of x over x squared minus 1 dx. So just like in the previous problem, I'm going to just find an antiderivative first. I'm dropping the bounds of integration. I just want to find an antiderivative of x over x squared minus 1 dx. I'm going to use a u substitution because the question suggests it. It's a good choice because x squared, its derivative x, also shows up in the integrand. So I'm going to let u be x squared minus 1. Which means du dx is 2x, which means that dx is du over 2x. And now I'm going to plug everything in. So this becomes the integral of x over u times dx, which is du over 2x, and the x's cancel. So this is the integral of 1/2 1 over u du. So I'm going to pull the 1/2 out of the integral. So this becomes 1/2 ln of u plus c. Plug the u back in, 1/2 the ln of x squared minus 1 plus c. Okay, so that's my antiderivative. So I'm going to go back to my definite integral, use that antiderivative to evaluate it. Okay, so the integral from 2 to infinity of x over x squared minus 1. So instead of going from 2 to infinity, I'm going to go from 2 to b and take the limit as b goes to infinity of x over x squared minus 1 dx. So that is the limit as b goes to infinity of, I'm going to take the antiderivative of x over x squared minus 1. Turned out to be 1/2 the ln of x squared minus 1, and evaluate that from 2 to b. All right, so that means first plug in the b. When I plug in b, I get 1/2 ln of b squared minus 1. And when I plug in the 2, I get 1/2 the ln of 2 squared minus 1, or 4 minus 1, which is 3. So as b goes to infinity, the ln of b squared minus 1 goes to infinity. So this becomes infinity minus a number is still infinity, which means it diverges. So the integral diverges.